So we talked about average velocity, and we said you can get the velocity or the speed from the slope of a distance versus time graph. Now we want to talk about instantaneous velocity, or, hey, what if the graph is curved? How do you find the slope then? So we have average slope versus instantaneous slope. As the slope of displacement time graph is equal to velocity, different slopes indicate different velocities or different speeds. Positive slope, going forwards, let's say, going north. When in doubt, my fallback, Lindsay, if they don't give me a direction, I always just imagine that positive is going forwards, and I'm imagining a car, because that's something I have lots of experience with in the real world. Speeding up, going forwards. What's the slope here? At rest, heading backwards. And heading backwards faster than that speed, but slower than that speed if I kind of estimate the steepness. Okay? What if I wanted the average velocity? Well, the average velocity of the whole trip, so we're going to add a little 5 right here. The average velocity would be the slope of that line. Doesn't care about what happens in between. It just wants the displacement. There's the displacement. That would be the average velocity. And what we're going to distinguish here today is between the average velocity and the instantaneous, right at that moment, velocity. Example 1 says, what's wrong with this graph of velocity of an object against time? Why is this graph impossible? Yeah. Now this is a velocity versus time graph, so you're at 2 speeds or 3 speeds at the same time. In Math 10, you would have said it fails the vertical line test, and I think I did my rant how a lot of the graphing in Math 10 is stupid because it's out of context. They give you, they say if it doesn't pass the vertical line test, it's not a function, which is really a vague explanation. You know what, Ryan? If it doesn't pass the vertical line test, it probably can't happen in real life. Something's gone wrong, which to me is a much better explanation in physics, okay? So right there, you're in more than one speed at the same time. Next thing we're going to be looking at, by the way, are velocity versus time graphs. That's going to be the lesson after today. All right. Example 2. At location X, which it seems to me is d, right about there. Which car is going faster at location X? How do I find faster? Well, the first thing I better figure out is what kind of a graph is this? What kind of a graph is this? Okay, position versus time, distance versus... So where does faster appear on this graph? It was the key idea from the last lesson. Slope. So when it says which car is going faster at X, what's it really asking me? Which car has a steeper slope? Okay. At location X, what looks steeper, A or B? I think A, yes? Is that okay, Jess? If you want to, you can write down steeper slope in your notes if you want to remember how we found that. Which car is going faster at location or time Y? I guess it's location, at time Y. What's that look like to you, I think? What can you say about those 2 speeds? What can you say about those 2 slopes? I think the same. Same slope, same steepness. Is that okay? Hey, which car is going faster at time Z? Anyone? Pardon me? Yeah, A? Steeper slope? Hey, at what point did car A catch up to car B? Yeah, in fact, you know what? I think my line X is a little bit bad. I think it's supposed to go exactly right. I have a feeling it's supposed to exactly go right through there. So at what point at time X, whatever the heck that was, where they cross? I think in Math 10 and also in Math 11, you solve systems of equations to find where they cross. And again, that's nice that you can find the points, but it's out of context. See, here, where they cross means something. Oh, they caught up. I think graphs in physics have more meaning than graphs in generic math. That's all review so far, in theory. So, now let's go to curves. The graph below represents the motion of an object. Okay? Before we get into answering the questions, let's just talk about what's going on here. It looks like, don't write this down, I'm going to muck this up. What direction is it traveling to begin with, forwards or backwards? Forwards. I'm going to ask you the same question. I want the same answer. I'm just going to phrase the question differently. What does the positive slope tell you about the direction that it's traveling, forwards or backwards? Forward. That's how okay, forwards. What can you tell me about its speed in that section? Constant? No. Speeding up, slope, what? Slowing down. How do you know? You're right. How do you know? Alex, like you said it. Sure. What can you tell me about the slope? It's curving, more specific. What can you tell me about the steepness? Bigger, smaller, or staying the same? What can you tell me about the slope? Increasing, decreasing, or staying the same? Decreasing slope. Okay? If you had to make a guess, what's happening right there? At rest. Okay? Going backwards. What happened right there? It went backwards past me at the start. If you were at the starting line, it went past you at the starting line, and now it's receding in the distance behind you, because there's the starting point, there's the starting point, point 0. Still going backwards. What happened right there? At rest. Okay, so how are we going to figure that out? Read along with me. It says this. Draw the slope or tangent line. I'd like you to underline the word tangent line, please. And I have to explain what this is, but to do that I'm going to stand up and I'm going to talk loud so the microphone on my computer still picks this up. Sir Isaac Newton wanted to find the slope of a curve, and what he decided was to find the slope of a curve, I could approximate it with the slope of something that we call the tangent line. What's the tangent line? The tangent line would be the shadow of this meter stick. The tangent line at point A would be about like that. The tangent line at point B would be about like that. The tangent line at point C would be about like that. The tangent line at point G would be about like that. Can you see what I'm doing? Is I'm imagining what the slope right there is and then extending it in my mind. We call that a tangent line. It touches the line right there and matches the slope of the curve right at that location. Sir Isaac Newton found a mathematical way to get it exactly, called calculus. How many of you know calculus? So we're going to have to use a ruler to do an approximation. Okay? So it says this. Draw the slope or tangent line at point B. At point B, I would take out my ruler, which here it is. I have my rulers here. And I would lay it flat. You guys can't see what I'm doing, but you'll see the lines suddenly show up. I would say about like that. Try and touch point B. I was a bit high, a little bit too high. But see, the nice thing is I can fix that. There. It's much harder to draw on this. This screen is really slick and slippery. It's much harder to draw than you realize. Okay? What about at point D? I'll use a different color. Point D right there. Now, what would the tangent line look like there? I would argue something like that. What I would not accept, Trevor, would be something like this. You're way off, okay? But I would accept a little bit of wiggle room. And if this was on graph paper, see, now what I could say to you is find the slope of your tangent line. Can you go rise over run? And that would tell you the instantaneous speed right at D. Be an approximation because we're not using calculus, but you'd be close. We can eyeball it pretty good. What about point F? Point F, I'll go with green. I would argue, I think point F is it bottoms out and levels out right there, I think. What does each tangent line represent? Well, first of all, it's matching the slope of the curve, but what is slope on a position or distance or displacement versus time graph? It represents what we call the instantaneous speed or velocity. Instead of the average, it's telling us right at that moment, that's how fast you were traveling right then. Instant, and then A-N-E-O-U-S, instantaneous speed. Hey, at what points on the graph above is the object moving most slowly? By the way, for some reason I wrote these questions, I doubled them, and I just noticed that now, but we'll answer part B, which isn't in here. Where is this object moving the slowest? Where this object has the smallest slope. Now, first of all, where is it at rest? Okay, let's answer that right here. We'll go B and F. Where is it moving the slowest? I would argue right before B and F because the slope is nearly zero. In fact, I would argue, Jess, it's slowing down, slowing down, slowing down, slowing down, coming to a stop. So just before it came to a stop, it must have been going really slow. Then it starts again really slow. It's speeding up, speeding up, speeding up, speeding up, going backwards, but it is a steeper slope. Speeding up, going at a constant speed, I think, for this section right here, backwards. Slowing down, slowing. I would say there's another couple of slow speeds right there. I'm not going to worry about answering that. I yoinked this from the internet because I can't do graphics like that. So it says, over what, question 4, over what intervals is this object speeding up, slowing down? Definitely slowing down between A and B. See how the slope is decreasing? I would argue speeding up between B and C. I know it's backwards, but the steepness is increasing, yes? Can you find me another section where it's slowing down? Where the steepness is decreasing? E and F? Can you find me another section where it's speeding up, where the steepness is increasing? I'm not sure. I think maybe, but I need numbers. There's one that is definite, it seems to me. Yeah, I think FG. It's okay. It's trickier now. There's curves. Next page. Yeah. Quick look, bunny. Over which intervals is this object moving with a nearly constant velocity? So B, C, F, G, A, B, E, F. Hey, over which section is this thing moving with a nearly constant velocity? Can you see it? I heard someone said it, yeah. CD, in fact, I might even argue almost CE, isn't it? Pretty close. So I'm going to actually go one step further. I'll say, how about C, D, E? I think that whole thing, you're going at a pretty steady speed. Okay, what's the velocity at time equals 0? Right here. Well, what I would have to do is I would have to extend the slope in my mind like that, and I would argue that right at time 0, I think that's the best approximate. If I could find the slope of that line, that would tell me the instantaneous speed at time 0. I'd need some graph paper and I need numbers to actually go rise over run, Courtney, but once I draw the line, I could. Is that okay? So how can you tell? extend the curve, assume it keeps going straight. I can definitely tell you that at time 0, the velocity was positive. We were moving forwards. When is this object changing direction? Direction comes from positive or negative slope, right? Well, just direction comes from a positive slope and a negative slope. Positive, 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 0, negative. Oh, you know what? It changed direction right there. Of course, it came to a stop for a split second and then threw the car into reverse. It changed direction at location B. And where else? At location F. This is negative slope, still going backwards. Negative slope, still going backwards. Negative slope, still going backwards. Less negative, but still negative slope, still going backwards. Did I say less negative? Slowing down. Stopped, threw it into forwards, and now going forwards again. I'm not sure what this is a graph of. Cars don't generally behave this way. You don't go forwards, backwards, forwards. Bumper car, maybe? I'd have to think about it a little bit. Okay, but definitely, I think at location B and location F. Is that okay? So, instantaneous velocity, finding the velocity of a curve at any point on that curve. We would like to find the velocity at time equals 4.0 seconds. Courtney, the first thing that I would do is I would put a dot right at, so here's t equals 4 right there. Since velocity is the slope of a d versus t graph, we have to find the slope right there. The problem is rise over run ain't going to do it. It's a curve. So what I would do is I would draw a tangent line, and I would argue that the tangent line to me looks about like that. Now, Jaden, if you drew your tangent line, I'd give you full marks. If you drew your tangent line, no, that's not even close, okay? But you're going to see in our answer keys for this work, there's going to be Cohen discrepancies. Mr. Dueck, I got 6.8, you got 6.7. Yeah, fine. Mr. Dueck, I got 6.8, you got 5.1. Go check your math. Okay. Now, how would I find the slope? Well, I would try going rise over run. This time I have some numbers. In fact, I think I'm going to extend. I think I go through right there. I think I go through, mine goes through 1, 6. And I think mine goes through, yeah, pretty close to 7, 1. Or is that 7? Hang on. 2, 4, 6. Yeah, each square here is worth 1. Yes? And 2, 4. So I think I can actually find the slope. I wrote here, by the way, a tangent line just touches the graphed line and has the same slope as the line right at that point. You can imagine a small car proceeding up the line or down for negative slope. I've seen some teachers, what they would do is they would have the students draw a little car, and this was the slope, the line between their wheels was the slope of the tangent line. Do I have any artistic skill at all, Connor? Say no. No. Can I draw cars? Say no. No. I'm not going to use that method, but okay, I included it in my notes. It's just embarrassing. Okay. What's the velocity at t equals 4? Well, for me then, what's my, first of all, negative or positive? Negative, I always put that in, Alex, because I've lost track of the number of times I've forgotten to put the negative in because I'm so concerned about doing the math, the rise over runway. What's the rise? Well, how high am I right here in my graph? 6. How high am I right here? 1. What's the rise between 1 and 6? Okay. -5. I got the negative already, so I'm just going to say 5. My run is 7 and 1. What's the run between 1 to 7? 6. For me, and yours might be a little bit different, Andy, and yours might be a little different, Sheldon, and yours might be a little different, Alex, and yours might be a little different, Alex. But for me, the way I drew this, and I'm kind of hoping with this freehand one we're close enough that we can use the same numbers. The instantaneous speed, right at 4 seconds, I'm going negative or backwards. 5 divided by 6, what is 5 divided by 6? 0.8666, I think. I'm going from memory. 0.8333333. So I'll go to 2 sig figs at 0.83 meters per second. By the way, what's the velocity at time equals 3 seconds? I would argue at 3 seconds I am at rest. Stopped. See it? What's the velocity at, when else am I at rest? I would argue I'm also at rest halfway between 5 and 6 seconds. I think I come to a stop at around 5.5 seconds. If you said 5.6, I'd take that. If you said 5.4, I'd take that. If you'd said 6.1, I don't think so. That's definitely already slanty going up. Okay. What if we wanted to find the average velocity between time equals 1 second and time equals 6 seconds? The average velocity. I'm going to do that in red. The average velocity would be from there to there. It would be the slope of that line. That's the average velocity. That's the rise over run connecting those two. You can see very different from the instantaneous velocity. Okay, I'm not going to find this, although you know what, I can freehand that a little better because that looks ugly. Use my ruler, Mr. Dueck. Go through the dots properly. There, that's better. I would go rise over run of that. Okay? For me, it's the red line, whatever, however you want to mark it in your notes. So, if I want, I found this picture online. It's black and white on your screen, but I think it still explains it an awful lot. If I want to find the instantaneous velocity, I would, suppose I wanted to find the instantaneous velocity at time equals 13 seconds. I would say 13 seconds is right there. Then I would lay my ruler down, and I would draw the tangent line. I already did. Okay? Then I would try and find some points where that tangent line went through. So I said it definitely goes through right there, and then I went up, 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 up. Yeah, I don't know if it quite goes through there or not. You might say it goes through 18,7. The person who did this online thought it went through 18,6.9. And now I would go rise over run. Let's do that right here. The velocity at 13 seconds is, what's the rise? How high are we right here? 6.9 meters. How high are we right here? 1 meter. What's the rise? That's loud. 5.9? Yes? You guys okay with how we're getting that? Right? Just subtraction. What's the run? 18 seconds. 10 seconds. And then I would change it to a decimal. What is 5.9 over 8? And I usually go to 2 or 3 sig figs. 0.74 meters per second. By the way, don't write this down, but a handy trick. Every once in a while, Courtney, you may find that the line that you draw doesn't go through any points at all properly. What you can do is, without lifting your ruler, just slide your ruler sideways and redraw the same line. Maybe now it'll go through some points, because that's got to have the same slope. Or, no, it still doesn't. Slide your ruler sideways. Maybe now it'll go through some points. That's a little trick of the trade. You may find just where you're drawing your line didn't go through anything. Very carefully, without lifting your ruler or bending it, just slide it left or right until you notice, that goes through some nice points. It's got to have the same slope. Trick of the trade. What about average velocity or average speed? average speed between 8 and 15 seconds, I would put a dot at 8 seconds, I would put a dot at 15 seconds, and I would just connect those dots, and I would find the slope of those dots, of that line between those dots, like that. What's the average speed? Now, the person who did this online used decimals like 5.6. I don't know. I would avoid that. I would try and go further or narrower until I found some nice points. But for now, okay, what's the average speed? And you'll notice I didn't put a vector sign on it, so it's speed. Did I put a vector sign? This one was velocity. And you know what? I should have put a vector sign because it's velocity. Although there's no direction, let's add a direction forward. There, now it's a velocity. Unless that R is supposed to mean right. I can't remember where I stole this from. I'll call it forwards. That sounds right to me. No? Okay. What's the rise here? 5.6, 1.0. What's the rise? Over. What's the run? 15, 8. Oh, that works nice. 7. The average speed is approximately 0.66. If you said 0.657, I'd take that. If you're trying to tell me 0.6571285, that's too many sig figs. There's no way, Alex, that we're that accurate. I would argue the best we're going to be is 2 or 3 sig figs, and even that's a stretch. So I'm going to go 0.66 meters per second. This is how we find the instantaneous slope. You lay your ruler down, which is why I said you needed a ruler or a straight edge, and you try and eyeball the slope. Now, Sir Isaac Newton found a way to actually do that exactly mathematically so that everyone gets the same answer no matter how well, you don't lay your ruler down. You calculate it. There is a way to do it. Take calculus next year. One more and I'm going to shut up. So we can use this approach to approximate the slope of a curve in order to find the instantaneous velocity. So here's a graph of distance versus time. It got chopped off by the photocopier on the y-axis. Can you fill in the word distance? Or did yours show up properly? Yours is there? Okay, mine just got chopped off. And this is in kilometers. This is going to be in kilometers per hour. That's okay. All right. Find the instantaneous velocity for every half-hour interval on the graph above. Okay, every half-hour interval, that's going to be here, 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 and here. Well, and I guess here should include 0 as part of the half-hour interval. So we're going to find 1, 2, 3, 4, 5, 6 instantaneous velocities. And I said, clearly show the line that you used and show your calculations so I know you read the points right. Okay. So let's do 0. I would argue that this has a slope of about kind of like that-ish, sort of. Mine, Courtney, happened to go nicely through that point right there, so I think I'm going to use that. Yours might not quite. Our answers might be a little bit different from each other. That's okay, as long as they're not a lot different from each other. So we want to find velocity, v, at what time? 0. If you do v and you put the time as a subscript, I'll clue in which one you're talking about. What's the rise? Well, for me, it's that point right there, halfway between 10 and 15. What's halfway between 10 and 15? 12 and a half. Take away 0 is my first height, all over, and my run is 1.5. Take away 0. I would argue when we started, we were already traveling 8.3 kilometers per hour. 8.2, yes, I'd take that. 8 point, in fact, you know what? I'd probably take anything from 7.9 to about 8.8, give or take. Is that okay, Court? I'll get the right units. This graph is kilometers per hour. I'll change colors. Let's do the velocity at time equals 0.5 hours. Half an hour in, 30 minutes in. How fast was I going? By the way, look at the graph. Half an hour in, are we going faster or slower than when we started? I'm going to ask you the same question. Half an hour in, I'm just going to phrase it differently, is the graph steeper or shallower than when we started? Steeper. Half an hour in, are we going faster or slower than when we started? In other words, if I get an answer less than 8.3, an alarm bell is going to go off. Ryan, I've typed something wrong. Right? Okay. I'm going to do my instantaneous tangent line slope. For me, it looks, and I tend to make these nice and long to really guarantee that there's a good chance that I'll go through a point. Mine looks, and I'm doing this one in black, kind of about like that. So I'm going to use this point, and ooh, I think I'm going to use that point there. Again, Sheldon, yours might be a bit different. What's my rise? Halfway between 20 and 25, 22.5 and 10. It's going to be 22.5 take away 10. There's my rise, 12.5 again. What's my run? So, ooh. What's each square worth? How many squares make up 1? Count. How many squares make up 1 hour? 4 or 8? 8. So each square is worth 1/8? Or each square is worth 0.125. I'll just jot that off in the margin somewhere. So it looks like this here then would be 7/8. Is that okay? Or as a decimal, 0.875. There's my right-hand one. 0.875 minus, and my other point is right at 0.5. Good. Now, if you're using your calculator, and for this most of you will need to, Hedrick, is there more than one number on the top of the fraction? Say yes. Is there more than one number in the bottom of the fraction? Say yes. Brackets around the top, brackets around the bottom. I'm going to go bracket 22.5, take away 10, close bracket, divided by bracket 0.875, take away 0.5. My instantaneous speed is approximately 33.3, I'll go 33 kilometers per hour. Is that faster than when we started? So I'm okay with that answer. Does that make sense on how we're doing that? Matt, you're okay with what we're doing? Okay. Do I need to do the rest, or are we okay with the 2 examples that I've done? Let's just answer the rest of the questions. B says, at what times has this person come to a stop? When has this person stopped? Okay. T equals 1 hour, and T, there's one more, I think. T equals, what is that? I guess 2.25 hours, 2.25 hours. 2 hours and 15 minutes if you wanted to change it to minutes. Okay. This is how we're going to do instantaneous velocity. There'll be a few of these on your test as well. When's the test? Don't know yet. So what's your homework? Finish off the material from last day if you haven't already. And then I have a couple of curves. This one is in meters per second. This is distance versus time for a walk. First, it just says describe the walk in words. What I'm really looking for is Forwards, backwards, speeding up, slowing down, or at rest? Any of those changes along the way. I would argue I start out going forwards, and then you can decide, do I start to speed up, slow down, come to a stop, at rest, or whatever. Find the average velocity for the entire trip, average velocity between 0 and 11 seconds, and then find the instantaneous velocity at those 4 sections. Then on the next page, on the back, we have distance versus time for walking a dog. Here it's going to be in meters per minute. Leave your answers in meters per minute. It's a weird unit, but go ahead. Okay. And then another curve here. See if you can answer those questions. And the answers are attached. Again, I made the answers in a hurry. Candy if you find a mistake. So I was hoping to give you a full half hour. I'm giving you 35 minutes. Woohoo! Play your cards right. No homework for your long weekend. Okay?